Welcome, everybody. I know it's a great introduction, although it makes me sound way more impressive and cool than I really am. That being said, I also just want to, besides thanking Mary, I want to thank the crew behind the scenes at MLOps. So shout out to David, Jen, and Valeria. Thank you so much for making this great. So another just bit of housekeeping: if you want to connect with me or check out the stuff I'm working on, you can scan the QR code, or those 3 URLs pretty much encompass anything you need to find me on. I'm happy to connect and go deeper if any of this really interests you. So my background, I think Mario kind of heated up for you guys. You know where I'm coming from. And this is more about a journey that I've been going on, and I wanted to share where I'm at. So why this talk? Well, it started off when I was at a Series A startup in the database world called SurrealDB. Really great product, really interesting guys, fascinating stuff. The play there was doing a multi-model, not multimodal, database. So if you can imagine all the different flavors of database in the world there are for doing different niche things, they did them all. The 2 specific ones that seemed to resonate the most were combining graph, knowledge graphs, which we're talking about, and vector search, semantic search. So hopefully you guys are familiar with embeddings by now. It's probably been beaten over everyone's head until you know exactly what I'm talking about. And I should say, if you do have any questions, please post them in the QA. I'll get to them at the end. Happy to go in depth on any of this stuff. So the notion was that the graph and vector was really resonating with our customers. And the reason really was, and I'll go into this a little more detail, is really on this notion of, at the time, doing RAG, which evolved into graph RAG, which is still a thing, but it's probably not talked about as much. But in general, AI really liked working with graphs. And also to get access to the graph using a vector to make it semantically searchable is very important. However, there was a huge bottleneck. So my need to get knowledge graphs in front of people to show the importance of this when they didn't know about it, or working with a customer who might have a lot of unstructured data, because most of the RAG implementations and AI implementations are pretty much built on unstructured data. That was a huge, huge lift. So how do I take a bunch of documents and turn it into a legible knowledge graph for a database, ultimately for AI? And the challenge is that I needed to come up with this stuff. So I went through a bunch of innovational steps of how do I get there? How do I run, walk, and crawl, walk, and run? And hopefully today, my goal is that what I've learned, I can share with you, at least as much as I can in the next 30 minutes or so. So I talked about this briefly, about AI being the thing. This is just an arbitrary Gartner number, but people can see these. The truth is, though, a lot of Gen AI projects just fail. A lot of reasons why. Now we're also going into the agentic era, full throttle. I won't even touch on that. But one thing I will say, and this is a consistent thing, me being a data guy, is usually projects fail because the data doesn't align to the goal. And AIs are just going to exacerbate that so much so. So the knowledge graph, why it's really interesting with AI in particular, it does 2 things. One, if you have a context window that's so large, you're going to have a lot of problems when you want to get as much data into that context window. So the more that you can condense it, the better, right? So if you have a knowledge graph and you can represent your data knowledge graph, you can throw out a lot of extraneous words. If you're thinking in sentences, and it could be expressed in a knowledge graph, much, much more condensed. B, you can go deeper and have the actual nuance explicitly stated to the AI, so it doesn't have to hallucinate all that. So what does that mean? Well, when you look at this AI world, you're going to have this notion of what I'm going to call an AI context gap. All the hallucinations that you have, a lot of just generic experience that you get because it's just answering from the mean and doesn't have access to a rich corpus where you'd like to put it into the context window, all that is going to create that gap, as it were. So knowledge graphs are one way to fill that gap. In fact, they're very, very powerful doing that. And I'm not going into all the details and have stats and all that stuff. But the reality is they just don't exist in a lot of businesses. So the question is, how do you get that knowledge graph in front of your AI? Well, this is what we're here to talk about. And this is a real MLOps challenge. This is where, machine learning and operations really come, is like, how do I continually get documents and unstructured data into a database or into some structure that AI can use. So this is how I went about it. This is just basically me talking about 3 different pillars of how you can think about generating knowledge graphs. One is the first thing I did, I think a lot of people do today, which will just be to throw an LLM on it. And you basically prompt the thing, you're like, hey, here's a document, please generate a knowledge graph, spit it out in JSON or some format that, and give it examples, and you can do all the prompt engineering around that. It works. And, you can get a really nice graph out and it'll start working right in front of you. However, if you want to get a little more precise and you want to have repeatability, then you're going to have to start playing with some, let's call it older school tech. So NLP, by the way, I hope everyone knows I'm talking about natural language processing, and you're going to get some really good results. Thing is, it will be a little bit more precise, but that also means that you're leaving a lot on the table, and you can also have it be, I won't call it hallucinatory, but you can get a lot of false positives out there unless you know what you're doing. And then there's this other notion, if you really after just pure speed and you have a lot of structured data, but the data itself doesn't have very good relationships between different nodes. And let me be clear, I probably should have said this. When I'm talking about knowledge graphs, there's really two elements that we should be talking about, nodes and edges. So nodes are entities in NLP parlance, so a noun, for lack of a better word, and edges are the things that connect nodes. So you can have 2 companies that are connected by an acquisition. You can have a company and a person be connected by working for the company. You can have people connected to other people because they're friends or their relatives. You can imagine that. So the reason why I should pause on this is the traditional database, or the traditional way that you would store data, is very easy to express those things as a notion of a join in a typical database parlance. However, the join itself is just a connection between 2 nodes. If you think of a node as being a row, you don't have any actual context, you don't have any metadata around that. And B, it's very hard to express in a traditional way to be able to recursively go through those nodes to nodes and different types of objects. A knowledge graph allows you to query that really, really quickly and just present it. And then you can spit out however you want for the AI. So going back to the notion of why databases search becomes very powerful. So if you have a traditional relational database, whether it's a data warehouse or whatever, you can express these joins. However, it gets very hard in order to go after nuances, and you want to find things where you have some kind of semi-structured data, or you have documents and you connect these. You can use full text search and semantic search, I should say vector search, in new powerful ways to go after that data and construct a knowledge graph independently. So if you think of those 3 different pillars, the reality is none of those really solve very well at the end of the day unless you combine them in different ways. So I'm going to be talking about hybrid approaches that you can start thinking about how to combine different techniques together. And ultimately, what I'm trying to get to is something like this. So if I have a bunch of financial documents, call it news, 10K filings, or any kind of financial data as an example, I want to be able to create a really comprehensive graph of how these objects and these entities are connected to each other with a very precise way. But also I want to get to the expanse of this, and I want to make sure that I'm doing things like BlackRock as a company. I'm getting all the entities that are actually BlackRock connected to each other, and I'm not getting weird things like multiple versions of BlackRock, which would have LLC or international or Black and Rock, or have rock music somehow connected. That's the challenge that we're trying to solve for here. So to go in a little more detail of the different techniques and how we see them. So we see the LLM approach. As I mentioned, it's going to be really powerful. Everyone sees how powerful LLMs are. It's gonna do very good at understanding like the nuances within a document, of understanding that DE for DE Shaw, if anyone knows finance companies, is not short for Deutsche Bank. It will know from context, and it'll be very smart at it. And it's also going to be able to pull out lots of information that you didn't even really consider. So you can think of that as a positive or a negative. It depends upon your actual use case. However, the challenge for a lot of people is going to be very costly and slow and noisy, as I mentioned. So if you have some real notion of high precision, goals, you're going to have some challenges. If you also need explainability, you're going to have some challenges. And if you imagine that you're looking at one document and it takes a minute to process, that might be good, but that could be horrible, especially in an agentic workflow where you might have 10 different agents all talking at the same time, and they're not running in parallel. This could be very, very challenging. So let's talk about some of the other solutions. NLP. It's really, really, it's a deterministic, it's not stochastic like an LLM, so it's explainable, which is really powerful for a lot of people. A lot of folks need to know that they run the code, it comes back with the same answer every time. You're going to get that with NLP. Even though it is machine learning and it's not just a deterministic, like this is definitely this, it's using a lot of techniques under the covers, and it's really powerful. But there's a problem with it. It's pretty brittle. It takes a lot of upfront knowledge about your corpus. It takes a lot of upfront knowledge about programming. It takes a lot of information that you have to continually make sure that your code is up to speed as your data changes. And that's a big limitation for a lot of folks out there. But this is an example of how I've been using it, and I've been using a lot more pattern matching recently than just being very greedy with all the pulling all the entities. So if you imagine that you have a document and you're gonna, and I'm using Spacey for this right now. I like to use either phrase matchers or matchers, and I can use that in such a way that I'm generally interpreting the type of corpus. So I'll keep using this analogy of financial filing. So I know that I want to pull out people. I only really care about people with important titles. So I want CEOs and I want COOs and those type of things. So that's how it's going to be able to hone in on sentences with those type of people in there. And I also want to just go after actions that are important to me in my analysis of financial statements. So I want to see partnerships, I want to see acquisitions, I want to see mergers. So if you think about all the general things that you want to talk about, you can actually use a LLM to help you generate like what's important in the type of stuff you're looking for. And that's one pass. Then after you pull out these sentences, I look at this in two different ways. So first, can I actually use the techniques within NLP to understand the sentence well enough that I can say that there's a real obvious connection between the subject and the object? And is that connection, do I have the grammatical way to actually parse out what the verb is? If I do, wonderful. Now I actually have a really strong two nodes and an edge. And I can pull in the entire sentence that's been pulled out, and that's going to be relative to that detected node to edge. I have all this information that's really wonderful. And sometimes, though, it's not very obvious to find that nice verb. So I have a fallback position, which will just be, hey, let's be dumb about this. Let's pull out whatever verbs are and see which one's the closest between the two. It's another way to get it, so I can get at least more data into the system. And once I have that, I'm still going through this NLP workflow, and I'm going to take all the entities that were discovered, and I'm going to kind of aggregate them in such a way that I can actually look at counts, and I can say also I have a confidence notion of if it was detected under a very strong confidence notion of like, hey, the sentence was actually properly parsed by NLP, let's give that a higher score. If it's not done that way, it's like the proximity type approach, well, let's give it a lower score. But if I detected the same relationship of, Bezos being the CEO of Amazon many, many times, let's boost that amplification. And with all that scoring that you can think of, you can come up with a rule of thumb of what you want to consider going to be a true positive versus a false positive, and just have a cutoff. And then obviously all of your negatives, which you didn't detect any of these, will just sit there. I'll get back to that later. Now, I want to talk about the database aspect of this. So as I mentioned, a lot of times the real challenge is connecting entities to each other within a database. And this is also going to be relevant from the NLP output to the database as well. But the trick here is that you want to go for something fast, and you want to do something where you're be able to pull out strings in I'll say a fuzzy way. The fuzzy matcher is not very good. But this is a really good series of techniques that you can do. if you know that you have a master data list or some kind of reference data, and you're trying to connect more unstructured, messy data to this. And by the way, that SQL statement is just pseudocode, but it's just basically saying doing full text search or form a vector search. One thing we also have to consider is that at the end of the day, we have a lot of entities, and entities could be any type of thing, but generally a lot of these entities, if it's person's names, whether it's Mr. or Junior, the first, the second, the third, whatever. If it's companies, you'll have things like LLC or Inc. or all kinds of different combinations of pronouns and all that good stuff. You want to kind of get rid of that so you can get to some ground truth of what an entity really is. So this is some examples, and I just say this in general. I will also say that your LLM is your friend. If you want to pull out a bunch of jargon words from a bunch of sample data, it's really good, and it can be overly expansive. So you have to mind your P's and Q's. But this is something that's a critical step for what I'm going to be. A bit about embedding algorithms. So I'm using fast text for this example. Generally, people think about embedding algorithms as being used to tease out semantic understanding. In this case, I'm using it as a classification problem. So I'm using a supervised approach of, so in this case, a bunch of firms and all the different ways that these firms can be represented. And then it's going to actually create an embedding model, and that embedding model can then be used to connect Microsoft to every different combination of misspelling of Microsoft, as opposed to connecting Microsoft to Apple or Amazon. Well, actually, Amazon's probably a bad one. To Apple or Dell computers, because even though those are all technology computers, companies, that's a semantic way. We're actually going after that Microsoft and all the misspellings and all the things we're going after. This is much more like how you would say these sentences are positive and these sentences are negative. It's a very similar approach. It's just a lot more than just good or bad. It's Microsoft and Apple and SAP and all the different companies out there. So this is really good. And now we can actually apply that to that output we talked about before, we thought were true positives. And then we can actually further process those in order to go after, hey, can we align these to our master data? And if so, great, it's a verified match. And if no, we have some options. We might want to throw them out. We might want to log them for later processing, or we might just want to say, like, actually, we want to be greedy and we want to add that as a new entity. That is a new company, and let's go ahead and add it. So, summing the key takeaways when we think about NLP versus an LLM, I'm going to sum it up in this is just an example. If I ran a process of pulling an NLP against a document pipeline, literally on my laptop with just a GPU, nothing fancy, I can run that thing in under 20 seconds and get good results, and they're very precise. If I do that same thing on an LLM, let's go after all of Google's resources and use Gemini, it could take well over a minute, and won't be the same result every time. Get me lots more results. In fact, some really interesting stuff. But again, it's not necessarily rinse and repeat, and it will be, relatively speaking, an order of magnitude more expensive. Not just a little bit, but you can imagine all the GPUs you can throw at something, and then you're eventually going to get diminishing returns. And I should mention, we should also note that all the tokens out there that we're paying per token right now, those are heavily subsidized. There's a world when, the companies of the world that will no longer subsidize once they have enough market share, and we're going to spend a lot more on inference. So we should be mindful, even if it's not expensive now, it could become much, much more expensive in future. Even if let's say the cost to generate LLMs keeps going down, inference is not necessarily going down at the same pace. We're just not paying full cost. When do you use pattern-based NLP? Back to that, is going to be when you have structured master data to align to, and you require explainability. Latency or inference cost is going to be a factor, and this is really talking about high volumes, and you might have regulated concerns as well, but this is a high precision goal. So spam filtering and not sending the wrong people to jail. Right? That's the challenge that we're working here. When using a LLM, so even if you have a master data set, you also want to grow it organically. You want a lot of, you're cool with having a bunch of extra positives. It's fine. And the relationships you're looking for are not well defined. You can't really explain it. And your corpus basically is very nuanced and is not homogeneous. So, it's not just financial firm data that's coming from 10K filings. You also have lots of disparate news sources and Twitter and all that stuff. This is going to be where you're going to have a lot of nuance. And this is a high recall, concern. So this is like, I want to make sure that your doctor is going to overly flag stuff just because you might be sick. That's a good thing. Fraud detection, that might be fraud. Let's make sure we get it. Those are the concerns that you have. Being mindful of time, let's try to breeze through this. So this is what I kind of talked about today, and I'm going to talk briefly about one little piece that I didn't mention, which is building custom models. So think of these are SLMs. And this is where it gets really cool. You can actually train these things and run them pretty small, and they can have better precision. It's still going to have a little bit of vagary, but you can think of this as being as part of the funnel of something that you connect to the output from your search or NLP processes, and to put it all together as a conceptual diagram. You start with your source document, you put it through your NLP and search practices, and then you can have an SLM that's been trained to actually look at those outputs and reclassify, refine, make sure that the sentence actually had the right object and subject, maybe make the verb a little bit tighter and all that good stuff. But then if you have all those false negatives out there and all the stuff that just didn't go through at all, you can have an LLM sample those and not necessarily write directly to your output. You can have it think about, hey, how can I change my rules engine for my NLP? How can I change my search criteria? Do I need to redo my embedding algorithm? So you can have those processes run offline and keep that high precision system up and running and still performant. And that's where I think we're going to see a lot of bang for our buck. So in quick little summary here, we know that if you want cost-effective scalability, use NLP and SLMs to really go after that, and you use expensive LLMs for the high-value tasks or training the system itself. If the enhanced precision and quality is going to go through, when you're putting this on the filter on the NLP output, and it's going to dramatically cut down on the false positives. And then it's going to also increase the reliability of your final data. And this whole self-improvement thing, I would say that this is like a pattern that we should all be considering for all of our systems in general. Let's think about LLMs and how you can look at them to look at your exhaust, your log data, and also your code or other systems and say like, hey, occasionally, can you make some suggestions of things we might have missed? What's going on here? This is not just about putting it into your dev cycle and having, Copilot help you code or whatever. This is about always being part of that full loop. And altogether, once you put these things together, you're going to have comprehensive coverage of a system that's going to be much more reliable. And I believe we have about 3 minutes left for any questions. So, Mario, did you see any come through on the wire?
So do you have any open source code available through this? What's the throughput?
I guess those are two questions. Open source code, yes. I do also have a closed repository because I'm still working on stuff, and I'm embarrassed because I haven't commented on a bunch of stuff. But my Git repository actually does have some stuff that's all related. Feel free to take a look there. I do a lot of sample code on embeddings and things like that as well. But what was the other part of that question? Sorry, Mario.
What's the throughput?
Throughput. Again, this is TBD because let me put it this way. It's really interesting. I feel like LLMs, they don't scale. So by that, I mean, if you give it a small document or you fill the entire context window, it's very hard to say like how long the thing will run before it gives you the output, because a lot of it's going to be self-referential. It's a bit of a black box. But on the NLP side, you can at least say like, hey, I know that a document of certain size will roughly take X with the same number of GPUs. A document twice as long will be roughly twice as long, depending upon memory and things like that. But you can actually do more planning when it comes to that. And you can say like, hey, I can throw more resources at this thing and it will get faster. And not just by in parallel running a lot of stuff. A lot of times latency isn't just about parallelization. It's about how long it takes to execute literally any of the steps individually.